Greetings, my name is Cheng-Yen. I'm glad to introduce our paper, Self-Supervised Pyramid Representation Learning for Multi-Level Visual Analysis and Beyond. Firstly, self-supervised learning is a task to pre-train deep learning models with unlabeled dataset. Most self-supervised learning previous work use contrasted loss, where we enforce the consistency between positive pairs of features and push the negative pairs apart. Self-supervised learning algorithms are evaluated by transferring the pre-trained models to downstream tasks, such as classification tasks. But most previous work is suboptimal to multi-level related downstream tasks because the comparison of representations are built at image level. The model thus fails to capture the more fine-grained information, such as the presence of objects of different sizes. Also, it's difficult for models to explore the dependency of objects. So, we aim at designing a self-supervised learning algorithm to facilitate multi-level downstream tasks. The two main challenges we solve in this work are listed below. First, to capture the presence of multiple objects at various scales, we use patch-based pyramid representation learning to extract information from image patches of various scales. Second, because it is important to explore the dependency of objects in multi-level settings, we seek to use cross-scale correlation learning to explore semantic correlation across different scales. As I mentioned, our proposed framework could be divided into two main components. In pyramid representation learning, we obtain two image pyramids with data augmentation, where each level corresponds to one patch scale. Image patches at the same level are then sent to feature extractor to obtain representations. For each level, we use an independent set of prototypes to serve as semantic cues. We then compute the probability vector P and vector Q, the prototype assignments. The consistency of P and Q is enforced by cross-entropy loss. The representation learning at other levels proceed in a similar way. The main difference is that only one positive pair exists in the first level, while multiple positive pairs are present at other levels due to the presence of smaller patches. The second component of our framework is cross-scale correlation learning. To leverage the information and correlation across levels, we aggregate the vector P at each level and pass line into a linear projection layer G. The consistency between the patch level vector P and the image level assignment Q is enforced by using cross-entropy loss. In our visualization, we show the dependency of prototypes from different scales. We select images from the same image level prototypes and predict the patch level prototypes for all the patches inside the images. We observe that patch level prototypes are fine-grained visual concepts which are related to the concept of the image level prototype. Here are the performance of our framework on multi-level classification on COCO and VOC dataset using only fine-tuned linear classifier. We outperform all the state-of-the-art methods in all settings. Our framework also outperforms most of the SOTA methods in object detection and instance segmentation tasks on COCO, which suggests the effectiveness of our method. In conclusions, we aim to pre-train the deep learning models with our self-supervised learning method to enhance the performance of multi-level vision tasks. With pyramid representation learning, we explore the information of objects across different sizes. We also use the cross-scale correlation learning to explore semantic information across image scales. This concludes my presentation. Thanks for listening.